Hi, so good afternoon. Hopefully you can hear me. I think Dr. Utkarsh, somebody else.
Yes, sir.
Yes,
Okay,
sir.
great. So should I share my screen now to start with my presentation, or would you have
Yeah,
like?
sir, let's introduction to the participants about your. So I welcome all the participants and experts to the next session of the day. I welcome our non-expert Dr. Arnab Chanda, Assistant Professor in the Center for Biomedical Engineering at IIT Delhi, and he is joint faculty at the Department of Biomedical Engineering, AIMS, Delhi. He is a PhD holder from University of Alabama, USA, and founder of BioFed Technology. Dr. Chanda has also worked as postdoctoral researcher at the University of Pittsburgh, USA. He is an expert in fabrication and mechanical characterization of tissue mimics and has developed artificial surrogates for human skin, muscles, brain, and arteries. He also holds 7 US patents. I request Dr. Arnab to start the fruitful session. Over to you, sir, now.
Yeah, thank you so much, Dr. Pooja, for the nice introduction, and thank you all for having me today afternoon. So I'll just take a minute to just upload my slide and then get started from there. All right, so. Is my slides visible? If somebody can just give me a thumbs up, please.
Yeah, your screen is visible, sir.
Okay, great. Thank you.
Oh, yeah, PPT visible.
All right. So my name is Arnab, and I am a assistant professor, like introduced for the Center for Biomedical Engineering in IIT Delhi, and also jointly affiliated with the Department of Biomedical Engineering, AIMS Delhi. So today I'm going to talk about development of artificial tissues. So first of all, let's understand what are soft tissues when we talk about soft tissues from an engineering perspective, like not from a biology standpoint. So soft tissue is very similar to a composite material. A composite material is usually made up of two or more constituent materials, which basically includes a hard fiber, such as a carbon fiber, which is embedded within a much more softer matrix. It could be of the form of epoxy resin or some other matrices. So soft tissue is very similar in the form. It has, in place of hard fibers in a composite, it has soft fibers in a softer matrix. So it's a soft composite basically. So tissues and organs are mainly all lumps of soft tissues, and they are made up of soft fibers, which are in the form of collagen and elastin fibers, and the softer matrix is an extracellular matrix. So over here in a figure, we are looking at the human heart. So the figure on the left is the heart matrix, which is the extracellular matrix, and this is a complex orientation of the heart fibers, which are going in numerous directions and also occur in several layers. So this is the human heart looked upon as a soft composite. So there are several types of soft tissues. They are not all similar if you want to go from one to another. For example, the skin, which is the most commonly occurring soft tissue across the human body and it's visible, has three layers. The first one is the epidermal or epidermis top layer. The second layer is called a dermis, which is the middle layer. So if you were to get cut and you start bleeding, that's basically when your dermis got injured. So epidermal bleeding doesn't really happen. So you have epidermis, dermis, and the bottommost part is the hypodermis, which is a blob of soft cutaneous tissues and kind of integrates with some fatty layers and muscles underneath the skin. So these are the three layers of the skin. Skin is highly anisotropic, meaning if you were to pull the skin patch of skin from one direction versus another direction, it's going to behave differently mechanically. So skin is anisotropic. There are several skin layers within the human body, which are defined by, if we look at the figure on the left bottom, defined by something called the Langer lines. So what that is like they are basically the fiber lines running through our entire body. And basically, if this figures which you're looking at 1 through 10 are basically specimens. So these are tensile or mainly tensile testing specimens, which you would test in a mechanical engineering lab to look at the material properties. Okay, so if you took the specimen in a certain direction, like if you reverse the direction versus like keep it upright, it is going to change the mechanical properties because the fibers are aligned in a different way with respect to that specimen, as well as if you go from one location of the body to another. So for example, like if you go from the facial skin to somewhere on the torso, it's going to behave very differently. Like these are mechanical. So that way skin has 3 layers and it's highly anisotropic. The second type of tissue which we have here is the brain tissue. So what happens in a brain tissue is it is composed of two kinds of tissue. One is called a white matter and second is gray matter. Brain tissue is often called transversely isotropic, meaning anisotropic is something which is very difficult to predict. It can have a locational effect versus also the angle effect. So if you have a 90-degree versus 0-degree, but transversely isotropic is categorically something where you have a 90-degree angle. Basically, if I pull something along the x-axis versus something along the y-axis, it's going to behave differently. But if it is along the z-axis, it's a plane of symmetry. So that's called transversely isotropic. And anisotropy is where you do not have too many planes of symmetry. So this figure here in the middle bottom is showing brain tissue anisotropy basically of a gray matter and white matter. Some tissue samples were cut through from a brain sample, and basically we are looking at some of the fiber lines here. The whitish part here is basically some of the fiber lines which is incorporating a very different material configuration to that system. The third type of soft tissue which is highly occurring in the human body is human artery. So human artery, So human artery is another very interesting soft tissue which has multiple layers but wrapped around each other. So it's not really coming in like multiple layers at one place. So these are completely circumferential layers, and there are some longitudinal layers as well. So overall there are 3 layers, and this is highly anisotropic. So if you were to cut a cross section, you would see the first layer, which is the internal layer, which is intima, the middle layer is the media, and the outer layer is the adventitia. Several layers have longitudinal fiber placement and several layers have coiled fiber placement. So it's extremely anisotropic and hard to predict the material properties directly. So this is just to kind of give an outline of how diverse soft tissue materials can be. And as we dive deeper into soft tissue surrogates or artificial tissues, these are some of the factors we'll have to keep in mind to mimic the correct way of soft tissue or the most accurate soft tissue. So the next comes, what is the need for artificial tissues? So we have introduced soft tissues. So why do we actually need artificial tissues? Why not get tissues itself, like from a cadaver or from somewhere, like from animals or whatnot? So one of the key factors why we need artificial tissues is the need for realistic surgical training. So there is a huge demand in medical schools and hospitals for soft tissues which accurately mimic the human tissues. However, cadavers and live human tests pose ethical and biosafety issues. So for example, back in the day, like there used to be something called a ballistic test, which we use for looking at how bullets, how much of a puncture a bullet really causes to the human body at different stages. So that is something which we look at. So in this form, what happens is like they used to shoot on a person directly and test it. So that is totally unethical, like that is totally unethical, not acceptable. So that's why soft tissue mimics are necessary. Second is cadavers. So cadavers also are not that easy to obtain. You need to go through a bunch of clearances and IRB approvals and whatnot. And also they pose a lot of biosafety issues, like you have to maintain them in a certain temperature and environment. Otherwise, they are going to go bad, or the tissue properties are going to get completely different, like from the actual human tissues, due to dehydration and whatnot. So these are some of the challenges which we have here. The second part is what is the need for artificial tissues in general? So we need artificial tissues, so forth, with material properties similar to the natural tissue. So that is the criteria number one for artificial tissues. Second criteria, which is not really obtained that often and very usually it's not really mimicked that well, is called the surface properties of the field. So this is an area which is a very new area of research and development where the surface property of skin or a certain tissue is tried to be made similar in terms of friction properties or how it feels, how much hydration does it have. So tissues are hydrated, they're not really synthetic all the way. So that's another area where artificial tissues needs to be developed. The third one is artificial tissues need to be biosafe. So we should not get animal tissues, for example, which have biosafety issues. So we are already dealing with the pandemic, and a lot of the things are occurring because of malplacement or maltreatment of how animal tissues are being handled or animal products are being handled. So biosafety is a very key concern when we are dealing with animal tissues that also go bad. The fourth and one of the very key marketing standpoint aspect is low cost price for developing countries. So there are some tissue based companies which are building artificial tissues. So I have to keep that in mind because my company also deals with something similar. So most of them are located in the United States and Europe, and they are not really priced for the Indian market. So if somebody asks for a small patch of, let's say, artificial skin, that would cost thousands of dollars, and that's not really a reliable training tool for institutes. So that's where we need to be able to develop artificial tissues which are low cost and priced for developing countries such as India. So these are some of the applications which we are looking at on the right figure, which goes from making a making a realistic model of the human heart, let's say, to do some kind of surgical training. So that can be done in a medical school or college, or in a very specific surgery where something needs to be tried before you go for the actual surgery. So those kind of models can be developed. Second part is better prosthetics. So most of the prosthetics so far are hard prosthetics. They don't have too much of soft tissue component to it. Like, so if we can mimic the human foot soft tissue, for example, like there could be better prosthetics. Third is biomechanical testing. So a lot of labs are interested to test soft tissues to validate, let's say, their computational results if they're working in the area of finite element or biological computations and whatnot. But most of those clearances are very difficult to get with human tissues. So if you had a soft tissue mimic, which is synthetic, for example, which you can just move around with, that is very easy to test, and you can use that to validate your experiments. Okay. So the next part is PPEs. So a lot of personal protection equipment needs to be tested on soft tissues to make sure they're comfortable. So that's another area. Fifth is sutures. So if somebody, that's one of the most common training aspect, like where you practice suturing on a certain tissue, because that's the main aspect of a surgery. So if we had synthetic tissues which are there for our training and we can keep on using it again and again without any maintenance or biosafety issues, that is perfect. So that's one of the key need for artificial tissues. There are some other areas such as plastic surgery, which for which we need a much more, biocompatible tissues. So I would refrain from going in that direction too much, because biocompatibility is an aspect which is kind of a very different domain to go for. But another key area is ballistics, as I was speaking of. Like, so ballistic testing, for example, there are a lot of things coming as non-lethal ballistics, specifically in the US. So they have come with bullet designs which are specifically meant to deter a crowd. Like, so let's say there is a huge crowd control needed, like at a certain point, you just don't randomly fire or shoot at people. So you can have certain bullets which will just hit them and kind of injure them to certain aspect, but they won't really get a fatal injury. Like, so that's something called non-lethal ballistics. So for testing of non-lethal ballistics and also testing of general ballistics, how it is performing, soft tissue mimics are necessary. Like, how does it travel through the different organs? How does it travel through the screen? So these kind of information can only be obtained if you had an artificial soft tissue. If you had a cadaver, it's very difficult to operate with that kind of a scenario. The last one is soft sensors. So a lot of we are moving towards a world of wearable devices. So lot of soft sensors can only be put or placed on soft tissue mimics. So if we do not have a soft tissue mimic which is similar to the human skin or something which similar to
Sir,
the
excuse
muscle.
me, sir.
Yes,
Whether you're
yes.
changing the slide, it is showing need for artificial tissue right now to us.
Yeah, yeah.
Is it the same?
Yeah, need for artificial tissues. That is
Okay,
correct. Yeah.
okay,
Thank you.
okay.
Yeah. Yeah. I'll move to the next issue. So these are some of the key application areas to kind of give you a perspective before we move on to how we actually develop soft tissues, and then we get to a much more mathematical form. How do we characterize that? So the next slide starts on that. So the first artificial tissue which we are going to talk about is artificial skin, the most widely studied material so far around the globe. So there is, unfortunately, what most of the researchers have been using so far are porcine skin, which is an example of pig skin, cowhide, polyurethane gels or cadavers to simulate artificial skin. There are very few artificial skin mimics which exactly mimic the material properties of the skin. So even though so much of research has gone into it, no surrogate or no simulant or no artificial tissues exist to date which can mimic the anisotropic mechanical properties of human skin. And mechanical properties of the skin, as I said, like also changes from one location to another. So can we encompass different variants of the skin simulant, which is very easy to make, which can have a property of, let's say, my facial skin versus somewhere else. So if you look at the graph here, we are looking at the human skin properties, which is given in the kind of skin orangish color. So that's the actual human skin property. This is stress versus stretch. Stretch is just 1 plus strain. So it's a stress versus strain. It is one of the common mechanical properties which you get when you perform a tensile testing on any specimen. So that's usually for somebody who is not from mechanical engineering background. So you can get a modulus of elasticity for a linear material, but these kind of materials are highly non-linear. As you can see, if you take a slope at a certain point, it is going to change continuously as we go up. So that's why this is called a non-linear material. So we should be able to use stress versus stretch or stress versus strain ratio, uh, stress versus strain profile, rather than going for a single value of modulus of elasticity or Poisson's ratio. So if we compare that with the porcine skin, which is being used currently in literature, and the gels and some of the other tissue materials, it is completely different. We can see the profiles are way apart. So this is where we came up with the first type of artificial skin and tried to mimic it as close as possible to the human skin. And this is something which is we have a US patent on. This is one of the artificial skin, and these figures on the right show some of the formations of the same, like these are different compositions which were built. You can cast them in any shape or size. This is a very specific synthetic polymeric material composition. So what was the agenda when we tried to build this artificial skin? How do we go about doing that? So the first and foremost agenda was, can we match the human skin properties with a low cost mass producible material? Can we choose a material which is very similar to human skin? And something which can be used in wound suture experiments for some validation. So some of the key usefulness of the synthetic artificial skin, which we ended up developing, I'll get to the development phase in a second, can be used for standardizing the suture practices. Like we can determine, so this is a product. The bottom one is a product which is a suture pad, which was developed by our company Biofit Technologies, and we had this in several nursing schools. This is material property of skin, all the three layers, exactly the same property how it should be, and we validated it against actual skin properties. This can be used multiple times to determine suture forces for a surgery, to standardize robotic surgeries, a lot of training applications. So training on suture practices for different wound sizes. So we have different wound sizes, skin tags, mold removal. So a lot of surgical applications can be used. And these are some actual skin tests which we are doing on the real skin, and we are taking some properties and trying to validate that. This is another property where we're looking at how well a suture is holding. Okay, so let's get to how do we build this actually. So we come up with different material compositions. These are all polymeric material, mainly silicon based, platinum cured silicon. So these come in specific shore hardness ranges. That's what we call from a technicality standpoint. So what we do is, the step one is we do a bunch of tests with different compositions. So all this plots in this graph, you're looking at this bunch of tests, which is going from a very compliant or non-stiff material composition to a highly stiff material composition. So we have gone all the way from the bottom to the high one. So wherever the composition or the hardness is low, that is what we are looking at the lower side. And on the higher side, we are looking at a much more stiffer curve of stress stretch. Same thing. Now, the second thing is we want to be able to compare this with the real skin, human skin properties. So real human skin, like I've said, is not a single plot because it keeps on changing from one location of the human body to another. So what we have come up with is, and this is based on literature as well. So this is the skin upper bound. This is the skin lower bound. So this is the actual human skin or the natural skin, where all it varies from. So any of our material compositions which we have prepared, if it falls in between this upper and lower bounds, we can call them as a synthetic artificial skin variant. Okay, so that's the way of iteratively making sure that we have a composition which is unique and which falls within the skin upper and lower bound and can be called a synthetic artificial skin. Apart from that, once this step is done and we have narrowed down to, let's say, 6 to 7 compositions or range of compositions where which can mimic the skin properly. The second thing which we do is we create a control specimen. Control specimen meaning one single specimen, and we run a battery of tests on that specimen to look at repeatability, several other properties, linear and nonlinear properties, ultimate tensile stress, which is the fracture properties, and the overall nonlinear behavior across a lot of different strain rates and whatnot. Okay, so that's the step two. The first step is we narrow down from a hit and trial kind of basis certain composition ranges. The second step is we take one of those key compositions and we keep on running repeatability tests. So this one, which is called 90-10, 90-10 meaning basically 90% of one chemical and 10% of another, which we narrowed down to. This is all patent protected. So we came out with this 90-10 composition, which we thought would mimic the bottom line or the skin lower bound. And we thought we could play with this and look at some of the repeatability tests and what is going on there. So all the error bars are basically pointing at the repeatability test. So we can see the synthetic material is extremely repeatable. So that's the number one. Number two is similar low and high strain modulus. So this is a term which we need to understand here. So like I've said, this is a highly nonlinear material, so you cannot have a single modulus or a linear property define this material property. So what we could still do is, and a lot of papers and literature have done that, we create a lower modulus and we create a higher modulus. We drop down a tangential line from the topmost point and one from the bottommost point, and we take the slope of that. So we compare that with literature. The third part is we look at this ultimate tensile stress. At what stress, higher value of stress, does this entire specimen break? So we are looking at a break point here, close to 16.23 megapascal. That is the stress ultimate. So this is another comparison matrix. And the fourth one is similar non-linear behavior. So that is already complied because we are looking at a behavior which is very similar. So this is your 90-10 control specimen, which is very close to your skin lower bound with a very high amount of correlation index. So this is correlating fairly well. So this is how we end up forming an artificial skin simulant, or an artificial skin development is taking place. There is another type of artificial skin which is worth discussing. This is called a hydrogel based artificial skin. So what we discussed earlier is a completely synthetic material. What we have here is to look at the feel property of the skin as well. So this is the second type, hydrogel based. Hydrogel meaning which has a lot of water content within it and also behaves like a polymer. So we are using porous hydrogels with similar to natural tissues. So if you look at any of the human tissues, they have a certain level of hydration. Human tissues are never dry. So we mimic that certain level of hydration with this hydrogel based tissue mimics, and hydrogel compositions are optimized. This is a much more difficult process than making a synthetic simulant. Like there are a lot of chemistry involved, something where we need collaborators. The other one was much more of a mixing and making a composition, but this is where it requires a lot of chemistry and it is difficult to really commercialize that quickly. So hydrogel compositions are optimized to obtain skin mechanical properties. So we are looking at the stress strain profile here. These are some chemical compositions, and this is one of the composition which we came out with, and that kind of mix close to the human skin. And here we are looking at some of the tensile and compressive properties. Another key thing which seemed important to us while we were building this product, and we're always looking towards commercialization. So how does this material really compare with what we have in terms of silicon? Like if it is going super high, this might not be something for India. So we try to look at the breakdown of the cost. So a 10 by 10 centimeter square of skin patch, which requires which has a thickness of 0.4 or a 40 cc of hydrogel with a certain density. We compared the cost. It comes out to be around 500 rupees per kg equivalent of silicon. So that's like basically a kg equivalent of silicon. So 1 kg of silicon would usually cost us around, like, let's say 250, 300 ish. So this came out to be around 500, which is like around 70 to 80% above that. Not that bad. We thought like this would be like 4 to 5 times. So this is how we do the cost benefit analysis of this as well. And we can incorporate this cost based data also in the chemistry and the optimization to reduce the cost further. So this is another strategy which we need to do in order to make this hydrogel based artificial skin. So this is still in process and it's in a research phase. The second type of tissue I'm going to talk about is a very interesting tissue called an artificial artery. So like I've said, artery is not a very straightforward tissue. It has multiple layers wrapped around each other. So we are looking here specifically at a patient-specific meaning, something which is specific to me or somebody who has an issue, who has some kind of a health or heart-based issue. And we are looking at the human artery of that specific person through some imaging technique and making that to a model. So this is a patient-specific 3-layer human artery surrogate or an artificial artery. The fabrication methodology includes a 4-part silicon, which is mixed in different ratios, and this comes with different compositions, and which we are simulating the 3 layers intima, media, and adventitia with that. So you can look at this very populated graph in the top. I have not zoomed this out because it's kind of difficult to see, but I'll just point towards some of the key highlights here. So we are basically trying to mimic the ranges of the intima, media, and adventitia tissue properties on the human artery using our different hit and trial methods of different compositions. And we are trying to pinpoint which composition falls very close within this range. So that's what we have done. Very similar exercise to the human skin. So this is as far as the material is concerned. So we have come up with one material for intima, one for media, and one for adventitia. So that is all great. So how do we make this artery now? So that is our step 2. So we took a MRI set of MRI image of an arterial section, and this was converted into a 3D STL model, and we 3D printed this. Okay, and when we talk about the MRI image of the arterial section, we are specifically looking at the arterial lumen. Lumen is basically the internal hollow part of the artery from which the blood flows. Okay, so we have this 3D printed lumen model. So we are going to grow the artery around it. Okay, so we are going to put the new materials around it. So we checked at the material properties, and we used a very unique method, which is called a time controlled dipping method. So this silicon based materials are basically coming out in liquid. So what we do is basically have this material like put out in a certain jar, and we can dip it in this material, and this has a certain solidification time. So let's say 15 to 20 minutes could be one time. We can have accelerators to accelerate that further. there are materials which have a time of 7 to 8 hours as well. So for this one, we are looking at within this time frame of 15 to 20 minutes, we'll have to dip this properly. So time control dipping, how does it work? So if we dip something in a very non-viscous liquid, it's going to fall apart, right? So how do we dip this to make sure there is a certain layer thickness, which is exactly the layer thickness of the intima media or adventitial layer? And please mind it, this is like very small layer thickness. Like this is, we are talking at certain microns, you know. So how do we mimic this certain micron based layer thickness? So through research. So what we do is we looked at different times of dipping. So basically what happens if you dip at 5 minutes? What happens if you dip at 10 minutes? What happens if you dip at 15 minutes? We found out a specific time. If we dip after that much time of mixing of our composition, the composition becomes viscous enough that you can get that layer thickness. So this was a very laborious work, like which took a while, and we finally found out that these are the times. This is called the time control dipping techniques, using the specific material compositions through which we can achieve the 3 layers over this Lumen 3D printed model. So with that, we came out with different arterial shapes and cross sections. So here this is a model which we developed. This has the intima, media, and adventitia, precisely very similar thickness to an actual human artery. So this is a zoomed in version. So how is this really artificial artery useful? So a lot of stent implantation procedures which are using for surgeries, you know, like if there is a heart blockage, can be done or practiced in these kind of an arterial system, arterial model, which can be developed quickly before actually placing the stent inside someone's body. So there is a phenomena called stent oversizing and undersizing. So a lot of the times what happens is your artery might be very thin due to clogging and whatnot. And basically the stent which you put through might be a very small size stent, so that it's not really opening up the artery properly. It could be a large size stent as well, which is opening up the artery way too much, and at certain instances also damages the arterial tissue wall. So to prevent that, a model could be built and the stent could be implanted here, and we can look at this before actually going for a surgery at a certain person, and this could be totally patient specific. So this was one of the key issues which we were trying to address while we looked at the artificial artery. The next issue is an artificial brain tissue. So there is no soft brain tissue artificial mimic which can mimic the mechanical properties of the brain tissue, gray and white matter, before this research was performed. So we came out with a fabrication methodology of mixing. Rather than a 4-part mixture, we came out with it because brain tissue is extremely soft. So we came out with a 2-part silicon mixture in different ratios, and we tested a bunch of we call it test specimens or coupons at different strain rates, because there is one aspect of it, like when you hit a concussion or like any kind of like head-based injuries are really fast. There is something called traumatic brain injury, which is very common area in the area of biomedical engineering. So that area also uses a lot of brain tissue based models to understand the effect of high strain rates or high impacts on the brain tissue. So we looked at varying strain rates for developing these tissues and went all the way from 2.5 millimeters per second to 30 millimeters per second. These are all displacement rates, by the way. And this is a tensile testing specimen. So these are some of the results. Just the key highlights are we are again trying to plot. So the first 4 plots here with the error bars, you're looking at the white matter, gray matter properties at the high and low strain rates. OK, so the low strain rate is a 2.5 millimeters per second and the other one is a 30 millimeters per second. So these are the actual tissue properties, and 70A 30B, 70A 30B, low, high, these all are different compositions which are tested at different strain rates. So some of the key findings which we saw was our specific artificial synthetic tissues have an insignificant effect of strain rates just because they're isotropic. They do not have fibers embedded within it. So the effect of strain rate is not really significant in this kind of aspect. However, in an actual tissue, we see a lot of effect of strain rate because of the alignment of fibers after a certain strain value. So this way we found out that our tissue is very different from a high strain rate standpoint or a different strain rate standpoint, very different from the actual tissue. So what we came out with was we came out with different compositions simulating different strain rates, meaning the same tissue property, when it is tested at two different strain rates, we have a different composition for that. So that's what we came up with, because the same composition cannot work very similarly in different strain rates for the same real tissue. OK, so this is some of our findings which we found from the artificial brain tissue mimics. The next issue is another very interesting tissue. This is called a calcineal fat pad. So this is one of the most important fat pads or fat layers occurring right underneath the human heel. And this takes all the loads of the human body while you're walking. So it's a huge load bearing component. This usually gets eroded over time and basically weakens up due to a lot of wear and tear. And over time, sometimes with diabetes or a disease called plantar fasciitis, like this can cause certain harmful issues, like, and basically this layer sometimes like just thins out, and basically then you're basically hitting on your calcaneus, which is your calcaneus bone, and then you have a lot of foot pain. So this is kind of the context of things. So calcaneal fat pad testing becomes really important sometimes for building of development of footwear and footwear insoles, which are used for mitigating such injury-based pains. So we came up with a fabrication methodology for 4-part silicon-based mixture with different ratios to build this calcaneal fat pad. We had a certain specimen size, and this is this specific tissue would usually undergo compression. So we are testing at compression. So we looked at different strain rates because depending on if you're walking or standing or running, this calcaneal fat pad will go through varying strain rates or varying range of impacts. So we looked at different strain rates to capture all that. We also looked at cyclic strain rates. So what happens when you keep on doing loading, unloading, because that is usually what happens on the foot. Like, it's not like I walk once in my life and sit down, like that never happens. I keep on walking, and basically this fat pad goes through a cycle of loading and unloading. So we also looked at some very high strain rates like 180 to 1800 millimeters per second, which are basically when you are jumping or going through a lot of really poor impact, like while running, let's say very fast running. So we did this range of tests, and basically we simulated using our new compositions, 3 different compositions. The first one is a healthy fat pad composition, which here we have a bunch of properties. First one is a healthy control, then the plantar heel pain. So we came out with 3 different. I'm busy in a meeting, please don't disturb. Yeah. Yeah, so sorry. There are 3 compositions here. So the first one is a healthy fat pad. So in this healthy fat pad, what happens is we have a range of force versus strain properties, which are taken from, literature and also physical testing. The second is diseased fat pad, which is a diabetic kind of fat pad. The third one is a plantar fasciitis based fat pad. So these are the 3 different fat pads which we tested on, and we came out with surrogate compositions which are mimicking the specific fat pad properties using the same agenda what we did earlier. All right, so the next thing is an cyclic and high strain rate tests. So what we did was next was we got a control specimen, which is called 60, 20, 10, 10. That is basically our composition. And we are calling this a healthy control. And we took this surrogate through a massive amount of loading and unloading cycles. And we compared that with our healthy control specimen. Okay. So what we found out was this is very similar in this aspect, like with this soft tissue properties, which we actually got from literature or from realistic tests. The second part is, just give me 1 second, please. Please disturb मत कीजिए, meeting चल रहा है. Sorry about that. So the second part which happens here is we are looking at specific high strain rates as well. So going from 1.96 to 1800 millimeters per second. And we looked at how the properties compare here. So the cyclic strain rate properties were pretty good. And the surrogate properties for the different strain rates also came out to be okay, like not that good. As we can see, the black dot lines compared to this one is not that close, but this does have some correlation, like at least this one is not going up or down. Okay. All right, so the next part which we came out with is an artificial anisotropic tissue. So we faced a lot of issues with going with an isotropic form where we just have a single material. It is very difficult to capture the anisotropy. So how do we capture the anisotropy? So we fabricated soft fibers, which is the definition of a soft tissue, soft fibers within a soft matrix, both made up of two different compositions of two-part silicon, and they were placed inside each other, and we came out with a composite property at a constant strain rate to compare with different values. So here are some of the specimens. What we controlled were 2-3 things. First is we increase the fiber volume fraction of the fiber amount, like within. So the inside blue part is much more hard or stiff. The outer part is much more soft. So the inside part we're considering to be mimicking a fiber, the outside part considering to be mimicking a softer matrix. So we looked at different fiber volume fractions, how much of the entire composite or the soft composite is really fiber versus how much is the matrix. The second is 2 to 3 different fibers. So we have a limitation of really placing a lot of small collagen fibers here, which I'm going to show in a coming slide how we address that aspect as well. But here we could look at a limited number of fibers. So we went from 2 to 3 fibers to look at if there is any effect of fiber spacing, and second is the number of fibers on the composite property. So we keep the same base material for the matrix and the fibers, but we keep on changing the number of fibers, the fiber volume fraction. And here what we do is 1 fiber, 2 fiber, and 3 fiber. This is also being done. And the fourth part is we are looking at different fiber angles. So what did we observe? Like when we increase the amount of fibers or the fiber volume fraction, very intuitively the material property is going to go up. So the true stress versus true stretch is going all the way up. It is getting more and more stiff. As this fiber amount is going down, it's going to be much more compliant. The composite becomes compliant with increasing fiber spacing. So basically, when we have more spacing between fibers, this is also fairly intuitive. The composite or the soft artificial material gets more and more compliant, meaning like it's not very stiff. The third part is the composite stiffens with increasing number of fibers. So what that means is when we have more number of fibers within a matrix, and this is fairly intuitive, like because fibers are much more stiffer, the overall matrix based property and the overall tissue properties just go up. The fourth is when we increase the angle. So if we are testing something in a uniaxial fashion and we increase the angle of the fiber from the direction of the load application, the material property in total just keeps going down. So when the fibers are completely aligned along that direction, that is also fairly intuitive from the knowledge of composites. So we wanted to verify all this knowledge from the composite using this soft composite anisotropic material which we developed, and see that what all can we capture using different material, using the same two materials and different directions and different fiber spacing and whatnot. Another interesting and the last soft tissue I'm going to talk about here is artificial tissue, and then we'll move to characterization, is an artificial conductive tissue. So this is the most advanced tissue which we came out with. So this is also anisotropic. This is conductive, and this also mimics the actual tissue very well. So how do we, I'm just going to quickly check to make sure everything is going fine. OK, great. So how do we make this? So the first step is soft matrix. It's a two-part soft based silicon. We cut short carbon fibers. So we get strands of carbon fibers, which usually comes in a roll. We cut short carbon fibers and disperse them within this media and mix them really well. That creates a lot of cross links, and that creates the um, component for the charge and the final, we can pass electricity through this. So mechanical and electrical testing is something we subject this to. So you're looking at a tensile test specimen where we have gripped this from top and bottom. So a tensile test is going on, and we are putting two electrodes at two different locations, and this is showing a certain value of resistance. So our strategy was, how can we reduce this resistance to a value that current can very easily flow, as well as at the same time have a material property which is similar to, let's say, skin or muscles. So this was a very challenging task, but we could optimize the system and make it happen. So this is a microscopic view of how the crosslinks would look like once you have kind of mixed this well, and this is taken a shape of an actual specimen. So we did resistance testing at different fiber weight fractions and stretches. So whenever we talk about fiber volume fractions or fiber weight fraction, we are looking at a fraction. How much fiber is there within the overall system? So we have fiber and matrix in this system. So let's say 0.5 of fiber weight fraction means we have a 50% fiber, right? So we tried to run a bunch of tests and look at what is the resistance at a common distance, at a common spacing of, let's say, 1 centimeter. If we took a 1 centimeter at this specimen or at any point, and a 5 centimeter spacing, what are the kind of resistances we are looking at? So the dark line here is the 1 centimeter, the 5 centimeter is the much more thinner line. So we are trying to look at resistance versus the fiber weight fraction. So the first deal was, we want to look at how can we optimize this resistance so that current actually flows. The next step comes as now we have optimized the resistance, how do we tune the mechanical properties? So this were two steps. So as a first step, we narrowed down that at close to 0.4 fiber weight fraction, in this case, this is by weight, the resistance falls drastically. So this is the resistance plot going down, and this is where it falls below 100 kilohertz and kilo ohms. And we understood that this is a reasonable number for passage of electricity. So we thought this could be a good starting point to consider that if the fiber weight fraction is around 0.4, that is good for this. Now we were trying to take this a little bit step up in the challenging mode. So what happens if you have an, so why do we actually need this conductive artificial tissue? What is the application of that? So I'll just touch up upon that real quick. So one of the key application is wearable devices. So we are moving in a world where we are wearing a lot of devices for monitoring different vitals, as well as they could be treatment based wearables. So very often than not, we have a lot of wires going through different parts of the body, which is extremely uncomfortable and difficult to manage. So we wanted to come out with an artificial conductive tissue, which can be used to make wearables, which are extremely comfortable, and you do not need wires. You can just plug in something at the ends, and we wanted to make it conductive and very similar material property to, let's say, my muscles or my skin. So that was the overall agenda. So the second challenge which we saw is a lot of these soft tissues, if we use them in wearable devices, would go through not 1% elongation, but up to 100 or 200% elongation. So there are a lot of moving objects in our body, moving joints in our body, which will take this entire wearable, stretch it to a very high amount of elongation. So what really happens? Does our material still hold valid for passing charge or current while that is happening. So we found out that is not the case. So if we have 100% elongation, once we release the elongation, there is some microscopic undulation which happens within this, which is called fiber agglomeration. That's how we call it. Basically what happens is the fiber kind of comes out of the matrix due to this huge pull, like material mismatch. And now this material is no more as conductive as this material used to be when this was subjected to 0% elongation. So now what we came out with, so what really happens when we have 100% elongation? How much volume fraction do we need? So we found out using optimization this value close to 0.7, which is fairly high in terms of fibers. That is how much we need to be able to have the same below 1000 ohms resistance for this one as well, like very similar current path as before. We need so much of elongation, so much of fiber weight fraction. For a 200% elongation, even more. If we look at the undulations here, this is going through even higher undulations. So what happens with an undulation exactly? So a lot of fibers which were cross-linking or sitting on top of each other in this mixture and creating the conductive path, they have kind of moved. So a lot of those crosslinks are really not forming as usual. So we need to increase the number of fibers so that even if there are few fibers which have moved here and there are still some fibers which are forming the crosslink. That is one of the key reasons we are trying to improve the or increase the fiber weight fraction drastically to still have the same conduction. So here we observe the fiber weight fraction needs to be super high, like it's about above 0.8, which is not really desirable, like because the specimen gets really stiff, it becomes fibrous, like so. That is how much we need for a 200% elongation. So we kind of concluded for 100% elongation, it's manageable. But for an application requiring 200% elongation, let's say if you're, somebody is running and wearing a wearable device, that might not be a suitable device. So that is as far as the artificial conductive tissues are concerned in terms of electrical conductivity. The second part is now that is all great. We have achieved electrical conductivity. We have found out fiber weight fractions which are optimized. Now, the second task was we wanted to do all these tests with this fiber weight fraction. So if we remember, we created fiber weight fraction has to be at least 0.4. Anything above that is good. So we started with, let's say, 0.4. And we looked at all the fiber volume fraction or fiber weight fractions above that and started comparing it. So these are all the specimens built with the same matrix, but different fiber weight fractions of the short carbon fibers. And the short carbon fibers are also at a very specific length, which we found out as a part of this research, that if it is below a certain length, the crosslinks are not enough. It is above a certain length, it is not really desirable. So the length was also optimized. So now we are comparing all the material properties, the stress versus strain with skin, muscles, pelvic tissue, and whatnot, like brain tissue. So there are a lot of arterial tissues which we are comparing this material properties of our compositions. And we found out most of the actual tissue properties we are able to mimic, if not very closely, because in few places you will see a curve is much more stiff, but there is always one composition out of all these which we can use to mimic a certain stress versus strain. So that is a very good news for us, like that we can create an artificial tissue which is conductive. We know what are the ingredients going into that. We can also tune its mechanical properties, keeping it conductive to any of the soft tissues, be it skin, artery, brain, muscle, or anything. And the third even nice thing is this entire tissue can be masked with colors. We can just put a color and you would not even see the fibers. So you could put a single color and this entire thing will look as if like there was nothing inside. So this is a good product strategy where we can have this for a lab to market transfer. So this was our idea. Okay, so that kind of finishes like the first part of the session, like where we are talking about artificial tissue. The second part comes the mechanical characterization for computational modeling. So basically these days we are looking at a lot of finite element models where everything cannot be captured through experiments. Very intricate details or what is happening at a certain location needs to go through finite element models. So how do we mechanically characterize soft tissues? So that is something to look at. And if we know this characterization methodology, we can make that happen for the soft tissue surrogates or the artificial tissues as well. So just briefly going through some of the mathematical versions of this. So the first and most common model is called an isotropic hyperelastic model. So basically in this model, what happens is there is something called a strain energy function, which is a function of invariance, which are function of stretches, which is different lambdas. Stretch is basically, let's assume this is a piece of tissue, or this is a block which is placed along the x, x1, x2 and x3, basically your x, y and z axis. And this is being pulled with a certain stretch, which is lambda millimeters, let's say. So lambda, when that is being pulled, then this is an isotropic material. There is a stress strain relationship, which is already there. And for a uniaxial test specifically, when there is nothing really happening on the other side, this is how the function comes out to be. So there are a lot of different hyperelastic strain energy functions. So this is called a psi, basically. So there are a lot of different psis which have been developed. And what are these exactly? These are all curve fit equations. So we were looking at the stress strain plots, right? All the stress strain plots coming out of like all the soft tissue tests, and we're comparing it with our composition based stress strain plots. All these equations. First one is, let's say, called Mooney-Rivlin, Veronda-Westman, Humphrey, Yo. These are all curve fit equations. What this does is this basically curve fits your stress versus strain or stress versus stretch. So where is the curve fit? I cannot see a strain and stress here. That is what happens once you take them through a bunch of differentials, and these are the hyperelastic stress strain relationships. These are energy functions. So we are looking at a stress we just call it Mooney-Rivlin because that model was developed by Mooney-Rivlin. So sigma is given by 2 times lambda square minus 1 by lambda. This is a nonlinear equation, C1 plus C2 1 by lambda. Here lambda is stretch, which is basically a strain plus 1. That is the definition. And sigma is your stress. So if I were to use any of my plots and just use this equation to curve fit that and find out the value of C1 and C2, then I know the hyperelastic material coefficients for that specific material. Okay, this can be done using different materials. They have been historically used for different purposes. Some of them have been used for skin tissue, some of them for heart tissue, and they've been much more successful in terms of correlation. Like by correlation, I mean there is a model fit parameter. How close is this to the actual plot? So some have achieved correlation of, let's say, 0.9, some have achieved more than 0.95, but it also differs from one soft tissue material to another. So these are some of the hyperelastic stress strain relationships which were being developed through time, and none of this were developed by me. So these are all literature based, and these are standard norms for characterizing or giving any information to a finite element model that this is what I've found out from my soft tissue test, tensile test or surrogate test. Please compare. OK. So the next step is a much more complex model, which is called a transversely isotropic model. I'll not get into too much of details. So in the earlier model, we were looking at just a single blob of material, no fibers, isotropic. Here we are looking at fibers. OK, so we are looking at fibers and matrix contribution, but there is something which is not there, which is there is no fiber matrix interaction. So the model does not understand that what really happens between the fiber and the matrix when there is a pull, because both cannot get pulled in the similar fashion, like they have different stiffnesses and material properties. If you pull one material more, the other will get pulled less. So that kind of interaction is not really captured in this model. So this uses the contribution, strain energy contribution of both the matrix and the fibers, and goes through a bunch of refinement steps. And then there is a final stress versus stretch equation and bunch of constants. So all the hyperelastic models, and this is under uniaxial test only. If there is a biaxial test condition, it would be different. We usually choose to do uniaxial test because it gets fairly complex to characterize something when it's in biaxial mode. So all the hyperelastic models, be it isotropic, transversely isotropic, or anisotropic, which I'm going to show you in a second, they all boil down to two things. They might look like very difficult equations, but they're actually very simple. They're basically curve fit equations. This is an equation between the stress sigma and the stretch lambda, and everything in between is a bunch of constants which needs to be found out, okay, through curve fitting. Third one is a novel anisotropic soft composite model. So there were no anisotropic models in the market, so we or in the literature, so we thought of coming out with an anisotropic model which clearly captures the fiber matrix interaction, clearly captures how much fiber is there, how much is the fiber volume fraction, and also the effect of different layers. So we wanted to put everything, like so far soft tissue has been characterized in a very idealized way. Like I've introduced soft tissue, it has multiple layer of fibers going in different directions. So that has not been captured with the existing model. So this model specifically, much more complex. Here we have fibers within a softer matrix, and whenever there is a pull or stretch to the matrix, the fibers rotate by a certain angle. We use different rotational tensors to bring this back. And I'll just quickly highlight the steps, not going into the mathematics part of it. Like, so there is something called a multiplicative decomposition of fiber along the fiber and the shear deformation in the other direction. So overall, we come out with a strain energy function where we also include a matrix and fiber volume fraction contribution. And then we finally club this all together. And finally, what we get through a uniaxial test is a model like this, which is your strain energy function. And the stress strain relationship comes out to be like this. Okay. Where what is the new thing which we have from before? We have a very simplified sigma versus lambda relationship, and we have C1 and C2. The new terms are VM and VF, which is so VM plus VF is equal to 1. They are the volume fractions, basically. So fiber volume fraction, how can we find out for a tissue? So we will have to make a we'll have to take a piece of tissue and like dissect it from the top and microscopically see like at a certain layer what is the distribution of that. So that's the only way of finding it. So that is the information which is fairly available, and we can throw in that VF and VM value into this equation, and it boils down to that same curve fit equation. We also added a factor of fiber orientation effect. So what happens if the fiber is oriented at a theta degree or a certain degree from the actual direction of pull? So in that case, what we have is a much more complex equation, but it all boils down to one single thing, that it's a stress versus lambda equation. This VF and VM terms are already known, and we have a theta which would be already known. So we can measure this fiber direction by just looking at the anatomy of a tissue. Like, so if you take a human heart tissue, you will see 3 or 4 fiber directions which are going, and based on how you cut your specimen, that is what defines the fiber direction. So this is your specimen. Let's say fibers are going this direction, so this is the theta. You can easily measure and throw this into this equation. That is an overall model. What happens is we have also extended this to multiple layers. So let's assume this is the entire tissue block, most realistic so far, which is multiple layers going in different directions, with every layer having a different fiber volume fraction. So every layer have a different theta, every layer have a different fiber volume fraction. So the final equation comes out to be like this, a sigma of everything, like all the energy equations are added for layers. But if you look at the non-complex part of it, it is again an equation between the sigma and the lambda. And everything in between, most of the VFs and VMs are already known. C1, C2, C3, C4, C5 are to be determined using curve fit, and theta is also known, like from before. So the soft composite has n fiber matrix layers. Okay, so this is the system. Mechanical property of each matrix. So every layer, the fiber and the matrix have the same property. This is very similar to our artificial conductive tissue. There we did not have the layers. Here we have different layers, which is capturing an actual tissue. But in any model, we have matrix and fibers, and mechanical properties of this matrix and fibers are the same. Only those directions are different, and the volume fraction of the fibers are different. So these are the two different things. All right, so the layers are assumed to be perfectly bonded. That is an assumption which we did. They are usually not in all cases. Sometimes there is a sliding or frictional effect between layers. Interaction between the layers is not modeled. The interaction between the fibers and matrix is modeled, but between the layers is not modeled. So that brings us to the third leg of our seminar here. So basically on this is all great. We have created a lot of different, artificial tissues. We have already characterized it using different models. But what are the key applications? How do we use this? So this is the third part. So the first application is understanding soft tissue damage and repair. So doing research on wound and suture. So how is this important? So most of the surgical training which happens is on wound repair and how to create the right amount of incision so that you can capture a certain amount of area to get in for a surgery, like let's say the human heart or any kind of very difficult surgery. So wound and suturing are one of the key aspect in terms of sealing a surgery and also opening a surgery. So this is the beginning part of the surgery and end of the surgery. So understanding what wound shapes to be sutured in which way in a standardized fashion is a very difficult knowledge to translate. So this is something which very young trainees might not know. This is something which comes with experience. A doctor or a surgeon like of 20 to 30 years experience would know exactly how to operate their needles and go for it. But a trainee would not really know this. The second part is what kind of wounds are very difficult to stitch in a certain way versus like what is the right way of stitching. This is also a knowledge which is not really that well known. This comes with experience. There are certain tricks of the trade which comes through. So this is one part of the puzzle. The second part is we are moving in the world of robotic surgeries, where the robot is not an experienced robot. It is whatever we feed information, that is what the robot does. So if we have a range of information on what is the suture size which needs to be placed, this kind of wound depth or wound shape, how it is to be tackled, if all this information is fed into that robot or model, then that robot can perform very efficiently. So that is what starts this kind of area of research where we need artificial tissues to train a lot of upcoming people like on training schools and nursing school for suture and wound training and also robots. So how can we do this without having a actual cadaver or soft tissue in hand? So we can use an artificial human skin, which we developed. We had different wound geometries placed on it. So these are you are looking at some microscopic images of a range of wound geometries. Few are common, few are uncommon. We have also categorized the wound geometries as long and short and top, center and bottom. This is something which might be difficult to understand. Which we are actually looking at these specimens, which are 5x2 specimens. Sorry, 5x1. So these are 5 centimeter by 1 centimeter specimens. So based on where exactly the wound is placed on this, so that's how we call it top, center and bottom. And we have placed on this wound something called an interrupted suture. So there are various techniques of suturing. Continuous suturing is what is usually performed. So you take a wound, you start from one end, you keep on suturing. Interrupted suture is when you put one suture at a time. So you put one suture at the end of the wound, one suture at the other end. You keep on putting different sutures and until the point when you seal it. So we have put interrupted sutures in this, and we have also come up with some hyperelastic based relationships using our models, which we have studied to characterize that how this normal specimen. So we are calling this a tissue phantom or the artificial tissue. That's the same thing. So this is a human skin tissue. This is a tissue with a wound. This is the same tissue with the wound which is being sutured. So what is the difference in the stress versus strain profile of this and how do we characterize this? So these were the two research important questions. So here are some of the results. The first plot on the left, we are looking at skin phantom with wound. So this is and tissue phantom, without wound and with wound. So what happens here basically? With wound, the overall mechanical property shifts downward, which is what we really expected, that even with the error bars, multiple tests are performed each time we do this. And one good thing about this synthetic artificial tissue is you can take this through n number of cyclical tests. Unless you really break it, you can run n number of cyclical tests with huge amount of repeatability, which is not really possible with an actual tissue. If you take an actual human skin and pull it, there is a very high chance that there is fiber dislocation happening inside, and the second time you test it, it doesn't give you the same result. So this is a very key thing with unique thing with our artificial tissues, where we can test them n number of times and also form different samples as we speak, So this is the overall property which we have seen with the tissue phantom or the artificial tissue by itself and the one with the wound. Then we started looking at what is the overall property, and these are all average based properties of the tissue phantom without the wound, with wound, and the one which is sutured. So one very interesting thing which we saw is skin phantom with wound. This is the skin phantom with suture. So this is the middle line which you're looking at. So we would expect something that very similar, that this is the actual tissue. This is the wounded tissue. This is the sutured repaired tissue, which is not as good as the real tissue. But one very interesting thing happened. Few of the specimens, if you look at the error bars, behaved much more stiff or better than the actual tissue itself. So this was a very interesting finding. And what does that imply really? So we started looking at, so should I get more sutures then? Like, is that the way to go? Like, should I just get more and more sutures and my skin will improve? That is not the purpose, like that's not the what we found out. We found out that if over sutures are placed, like too many sutures than needed are placed, it can make the entire skin extremely stiff than the natural tissue. So we do not really want to go beyond the natural regime. More stiff is really not good. So that implies another very research objective like here, that whenever a suture is being done, over suture is not happening. So how does a doctor really know if he or she is over suturing or under suturing? That is very difficult to know right now. So this is the only way where we can research in a testing laboratory and actually see what are the different suture fashions and understand what is the thin line between the lower and upper limit for the over and under sutures. Then only we can inform a doctor that don't go beyond, let's say, 5 interrupted suture for a wound length of, let's say, 3 centimeters. So these kind of information a doctor would not know. So this is something which we intend to convey through this research. Another thing, getting much more deeper into the research into this wound suture geometry. Here we do not have sutures. So one very key aspect is when somebody goes for a surgery, like in a very complex organ, like let's say it's a stomach based surgery where you have a lot of other organs interfering in between, and the surgeon needs to cut a certain incision or shape so that he can enter his instruments and basically do the surgery. So what kind of incisions or shapes are desirable? They are also kind of wound. So wound is something which happens, and this is something which you create. Incisions is something which you create, but mechanically they're very similar. So we are trying to look at what really happens if there are different incision shapes. And how have we looked at it? We use something called a digital image correlation. So we take this specimens, which are all the same. We create these different wound shapes and we distribute something called a paint-based spray, very fine and thin spray, which is placed here, which places something called irregular speckle patterns. We call it speckle patterns. If you can look here, this is like white dots kind of pattern, irregular speckles. And what we do is once we have the speckles, we put this in a tensile testing rig, and we run a normal tensile test, and we put a video, very high megapixel video camera in the front trying to capture this. So what does the digital image correlation do? When we do a post-processing analysis with this video, then it can clearly identify the displacement of each one of these particles, how they're displaced from here to here, and make the entire strain field. This is a very advanced technique which is used for internal characterization of tissues and external characterization of tissues at a very zoomed in and very specific level. So this cannot be done using normal experiments. Normal experiments will give us global properties. This is the only way of trying to find out what happens in the periphery of this wound. Do I see certain locations which are highly stressed? Because what is the implication of that? If certain locations along this incision, which I'm planning to create, let's say I'm the doctor, is highly stressed, then there is a very high chance of tearing from here. That could be extremely painful. So I want to be able to create incisions which are unique and they are not going to tear further. So how can I get that information? I cannot put a digital image correlation in my surgical ward. Like that's not possible. So this can only be done through a research biomedical engineering or mechanical engineering laboratory where we're looking at the pinpointed soft tissue. Look at some of the results. So this is one of very common wound shapes which we are looking at. And this nice colorful lines, what we are looking at is the strain field, which is occurred due to what was done using the tensile testing rig. So basically, if you look at t equal to 2 seconds, so this is at the beginning of the test, just at 2 seconds. This is 24 seconds after the test. This is, I cannot really see it here. This is sometime much more later. I think that's kind of taken aback. But that's at a much more later stage. So these are different time frames. So this is while the tensile testing is happening, and what is happening during that time frame? There is a certain stress buildup here. You can see there is a slight curling and not stressed, like I mean strain. So there is a huge strain buildup along this location, and wherever there is strain, there is stress. Like so, we have a high strain buildup here. So what we observed at a later phase for this soft tissue mimic experiment is this part actually got torn off. Like so, there was a proper tear here, and the entire specimen just got damaged from here. So these kind of aspects are very difficult to look at a daily basis. So this is something which you can only achieve if you have a artificial soft tissue. Why can't you do this with a normal tissue? The paint will first of all not stick to a normal tissue. The normal tissue is not very difficult to operate in terms of digital image correlation. So you can only do it with a synthetic material. So this kind of research can only be performed with artificial tissues. So let's zoom in for a second, like into what we're looking at the periphery of this. So what this digital image correlation gives you is the strain at any point. If you, I have placed 4 points here at the periphery of this initial wound or incision. So I'm looking at what happens at this P0, P1, P2 and P3. So I can see P1 clearly is going super high, and that is where the high strain is building up. So this is much more better zooming into the results. So what happens? So strain build up around the wound shifted to left. So that is one thing which we saw. Initially, there was a strain kind of uniformly build up. There was a left moving because this part was weak. Tearing was observed with time. Tissue curling was observed due to strain buildup and tearing on the left. So this is one of the key things to observe. And so how is this implementable to an actual incision which we create in a surgery? So in a surgery, what this slide gives us is avoid these shapes of the wound, these kind of elliptical shape which has an eye to it. We call this pointy location as an eye to it, to be avoided for any kind of surgery, because every muscle or every tissue on our human body has a natural tension. So there is a natural tension of pulling apart. So if you ever had a wound anywhere, you would see by nature, if you place something like, when it is healing, your skin is curling a little bit on the side. The reason for that is your skin has a natural tension. So it's trying to pull that. It's not trying to heal that. So basically there is this pulling effect. So that might call this to tear. So we try to avoid this tear. Another application is the, this is called a hernia mesh testing. So what is really a hernia if for the general public? So I think hernia is basically a prolapse or a protrusion which happens when an organ tries to come out of a fat layer due to some kind of weakness in the fat layer itself. And this is extremely painful, usually happens in the abdominal or stomach area. And this is a layer of muscle. So the way this is treated is hernia is treated is basically this herniation part is put back surgically. There is an incision which is created. This is put back, and there is a prosthetic mesh which is placed along this liner so that to create a hammock so that this hernia really doesn't come back again. And there are sutures placed here to hold this together. So close to we are looking at 3 zeros, 6 zeros, 2 CR, 2 crore of hernia repair surgeries are conducted per year, like all around the globe. So hernia surgery with prosthetic meshes are not really reliable. They are very well known to cause pain and infection, which is more of a biological issue. The more of a loading or a mechanical issue is a hernia reoccurrence. So very often then what we observe is hernia tends to come back.
Chanda.
Yes. Hello. Hello. Can you hear me? Is there a question?
Sir. We can hear you. Somebody.
Yeah, it will take me 1 or 2 minutes to finish up. Then
sure.
Take questions. Okay, so how do we test this mesh? So this mesh goes through a lot of failures. So there has been a lot of dry and wet tests, which does not really have a role of the soft tissue. So what they do is they take this mesh and pull it in different directions and try to know what is the stress strain profile. But that is not the key problem here. The problem here is the way this mesh actually interacts with the soft tissue. That is where the problem is. The way this mesh actually detaches from a soft tissue, or where exactly what is happening, that is where the problem is. So there is a lack of mesh and human tissue interaction tests, so which is happening. And reason is lack of human tissues, which can be an abdominal tissue. If I just want it, I cannot pull it out from somewhere and put it with a mesh and test it. So a lot of tests are being conducted on animal models, which are not very fair, because the material properties of the animal tissues are very different from the human tissues. So just to kind of quickly run through what we did here was we came out with an artificial tissue phantom. We placed a mesh specimen, we sutured it like it would be, and we also, using the characterization model, which we placed here, an isotropic model, we also placed material properties and created a finite element model, which is a zoomed out version of this. So these are the soft tissues, these are the sutures, these are the prosthetic meshes. Okay, these were tested experimentally and computationally at different strain rates. And we found a bunch of results encompassing which is the load bearing component. Like, for example, is it the tissue or the mesh or the suture? Where exactly is this failing, this mesh tissue interaction in a actual mesh? So we looked at various stretch ratios and found out that for a stretch of less than 1.5, tissue is the major load bearing component. For stretch more than 1.5, the prosthetic mesh underwent permanent deformation, and several other solutions from here, which are very key findings, which cannot be found out from a non-lab research. The last finding which we saw is a very unique thing. We saw that the unit cell design of a mesh. So we zoomed into this mesh, right? So we looked at this unit cell design of the mesh is a very key component which causes the mesh failure. So if the unit cell is a certain shape, we have a huge stress or strain distribution at a certain location only, which keeps on repeating itself across the unit cell. So what we found out was if the unit cell can be properly tailored, because there are a lot of different meshes out there in the market, then we can achieve lower mesh failure rates. So that is the overall conclusion from this research. So I'll go through the final conclusion, not taking any further time. So we have looked at ethical and biosafety issues associated with cadaveric and live human tests. That is the key requirement for artificial tissue. So we need realistic and low cost artificial tissues for surgical training, specifically in India, and abroad also it's widely required. Most research artificial skin, that is the most commonly researched element, and basically these are synthetic and hydrogel based, so something which we came out with. We also came out with different artificial compositions for artery, brain, fat tissues, and also anisotropic and conductive artificial tissues, which are unique in their own forms for biomechanical testing and also for wearable devices. We also studied some of the mechanical characterization laws and mathematics for comparison and computational modeling across the real tissue and the soft tissue variant. And we also looked at some of the surgical applications relating to wound suture and hernia mesh testing for the artificial tissues. So that is our overall length of things, and that is why artificial tissue is really important. So that will be all, I think. Thank you. Any questions?
Thank you so much, sir.
Thank you.
I request all the participants, if you have any question, you may feel free to ask Arnab, sir.
Might have been a long presentation, so no questions. Okay, we have one question.
Yes. So thank you so much for this wonderful session
Sure,
about
sure.
artificial skin and its various testing. We are very
Absolutely.
thankful for your presentation.
Absolutely. Thank you for having me, and thank you for all for being here. I would be happy to share the presentation with, I think, the
Sure,
concerned
please,
person.
sir.
And yeah, if there are any questions, feel free to email me.
Sure, sir. Thank you, sir.
Okay, thank you.